myself, Dr. G.D. Verma, Associate Professor in Department of Physics. In this lecture, I will discuss the basic theory of interference of light, where I will discuss the conditions to get interference light in the laboratory, and I will also discuss some of the famous experiments which are used in the laboratory to study the interference phenomena. First, I will discuss what is interference. So, when two identical waves overlap at a point in space, the combined wave intensity at that point can be either greater than or less than the intensity of either of the two waves. This effect is called interference. If the resultant intensity is greater than the intensities of the individual waves, the interference is called constructive. On the other hand, if the resultant intensity is less than the intensities of the individual waves, the interference is called destructive. Whether the interference will be constructive or destructive depends on the relative phase of the interfering waves. If two identical waves arrive in phase at the same point in space, that is, they line up crest to crest and trough to trough, then the amplitude of the resultant wave would be twice the amplitude of the component waves, as shown in the left panel of this figure. This is the condition for constructive interference. Now, if the waves at the point of consideration line up crest to trough and trough to crest, the amplitude of the resultant wave will be 0, as it is shown in the right panel of this figure. This is the condition for destructive interference, in which two waves cancel one another's effect at the point. Although I have considered here the interference of two waves, but in principle any number of waves can interfere. The amplitude of resultant wave can be determined by using superposition principle, first enunciated by Thomas Young. According to this principle, if a medium is disturbed simultaneously by any number of waves, the instantaneous resultant displacement of the medium at every point at any instant is the algebraic sum of the displacement of the medium due to individual waves in the absence of the other. Here, it should be noted that modification in intensity takes place only in the region of crossing of waves, and out of the region of crossing they move as if nothing had happened to them. Now, let us consider the superposition of two sinusoidal waves of same frequency at a particular point. Suppose the displacement produced by each of the disturbance separately at the point are given by x1 t is equal to a1 cos omega t plus theta 1 and x2 t is equal to a2 cos omega t plus theta 2. Here a1 and a2 are the amplitudes of the waves, and displacement x1 and x2 are in the same direction. Theta 1 and theta 2 are their initial phases. Now, according to the superposition principle, the resultant displacement x would be given by x1 plus x2, and if we substitute the value of x1 and x2, we get a1 cos omega t plus theta 1 plus a2 cos omega t plus theta 2. After simplification, we will get x is equal to a cos omega t plus theta. From this equation, it is clear that the resultant disturbance is also simple harmonic in character, having the same frequency but different amplitude and different initial phases. In other words, the sum of two simple harmonic motions of the same frequency and along same line is also a simple harmonic motion of the same frequency. We can show that the amplitude A of the resultant wave is given by root of a1 square plus a2 square plus 2a1 a2 cos theta 1 minus theta 2, and the initial phase of the resultant wave theta is given by tan inverse a1 sin theta 1 plus a2 sin theta 2 divided by a1 cos theta 1 plus a2 cos theta 2. Thus, the resultant amplitude A depends upon the amplitudes A1 and A2 of the component waves and their difference of phases theta 1 minus theta 2. Here we have used algebraic method to find the resultant of two harmonic waves, but the resultant can also be obtained quickly by graphical method. This method is more useful when we have a large number of superposing waves, as we will see while discussing the phenomena of diffraction. So, to obtain the resultant of two disturbance x1 is equal to a1 cos omega t plus theta 1 and x2 is equal to a2 cos omega t plus theta 2 by the graphical method, we draw vectors OP and OQ of magnitude a1 and a2 respectively, such that OP and OQ makes an angle theta 1 and theta 2 with the x axis respectively, as shown in this figure. Here, if we assume that vectors OP and OQ rotate in clockwise direction with angular frequency omega, then the x coordinate of OP will be a1 cos omega t plus theta 1 and that of OQ will be a2 cos omega t plus theta 2. At t is equal to 0, the rotating vectors are at point P and Q. We use the law of parallelogram to find the resultant OR of the vectors OP and OQ. The length of the vector OR will represent the amplitude of the resultant wave and the angle theta that OR makes with the x axis is the initial phase of the resultant wave. Further, as the vector OP and OQ rotates on the circumference of the circles of radii a1 and a2, the vector OR rotates on the circumference of the circle of radius OR with the same frequency. From the triangle formed by a1, a2 and a, and using the law of cosines, we can find the amplitude of the resultant wave A is equal to root of a1 square plus a2 square plus 2a1 a2 cos theta 1 minus theta 2. From the figure we have a cos theta is equal to a1 cos theta 1 plus a2 cos theta 2 and a sin theta is equal to a1 sin theta 1 plus a2 sin theta 2. With the help of these expressions, we can obtain the expression for the initial phase of the resultant wave. Here we will get the same result as we have obtained earlier using the algebraic method. Thus, if we want to find the resultant of two displacement, then we must first draw a vector OP of length a1 making an angle theta 1 with the x axis. From the tip of this vector, we must draw another vector PQ of length a2 making an angle theta 2 with the x axis as shown in this figure. The length of the vector OQ will represent the resultant amplitude and the angle that it makes with the x axis will represent the initial phase of the resultant displacement. Now, if we have third displacement x3 equal to a3 cos omega t plus theta 3, then from the point Q we draw a vector QR of length a3 making an angle theta 3 with the x axis. The vector OR will now represent the amplitude of the wave resulting due to superposition of x1, x2 and x3. The angle theta made by OR with the x-axis will be the initial phase of the resultant wave. Now I will discuss the conditions for constructive and destructive interference. As we have seen, the amplitude of the resultant wave in terms of amplitudes and the initial phases of the interfering wave is given by root of a1 square plus a2 square plus 2a1 a2 cos theta 1 minus theta 2. Now let us represent the phase difference theta 1 minus theta 2 by delta. So from this equation it is clear that if the phase difference between the waves delta is equal to 0, 2 pi, 4 pi or in general 2n pi, where n is equal to 0, 1, 2, 3 like that, then A equal to A1 plus A2. From wave theory we know that phase difference of 0, 2 pi, 4 pi etc. means the waves are in phase. Thus, if the two displacements are in phase, then the resultant amplitude is the sum of the amplitudes of the interfering waves. This is known as constructive interference, and this will be obtained when delta is equal to 2n pi, where n is equal to 0, 1, 2, 3 etc. On the other hand, if the phase difference delta is equal to pi, 3 pi, 5 pi, that is in general delta is equal to 2n plus 1 pi, where n is equal to 0, 1, 2, 3 etc., then A is equal to A1 minus A2. That is, if two displacements are out of phase, then the resultant amplitude is the difference of the two amplitudes. This is known as destructive interference, and the condition for this is delta is equal to 2n plus 1 pi, where n is equal to 0, 1, 2, 3 etc. Since phase difference delta is equal to 2 pi by lambda into path difference, we can also write the above conditions for constructive and destructive interference in terms of path difference. Suppose two waves initially in phase meet at a point after traveling different paths. At this point, there would be constructive interference if the path difference is equal to n times lambda, and destructive interference if path difference is equal to n plus half times lambda, where n is equal to 0, 1, 2, 3 like that. So now I will discuss the variation of intensity of resultant wave as a function of phase difference. As we know, the intensity of a wave is proportional to its amplitude, and proportionality constant is taken as 1. Therefore, the intensity of the resultant wave I is equal to the square of the amplitude A of the resultant wave. So we can write intensity of the resultant wave I equal to I1 plus I2 plus 2 into root of I1 into I2 into cos delta. Here I1 is equal to A1 square and I2 is equal to A2 square are the intensities of the interfering waves, and delta is the phase difference theta 1 minus theta 2 between them. Since the maximum and minimum value of cos delta are plus 1 and minus 1 respectively, therefore the maximum intensity I max will be equal to root of I1 plus root of I2 whole square when delta is equal to 2n pi. The minimum intensity I minimum will be equal to root of I1 minus root of I2 whole square. This occur when delta is equal to 2n plus 1 pi, that is when waves are out of phase. If the amplitude of the waves are same, that is A1 is equal to A2 is equal to A, then I1 will be equal to I2 will be equal to I naught say. In this case, the resultant intensity I will be equal to 4a square cos square delta by 2, or this will be equal to 4 I naught cos square delta by 2. In this case, the maximum intensity I max will be equal to 4 I naught and the minimum intensity will be equal to 0. This figure shows I versus delta plot. From this figure it is clear that when two beams of light arrive at a point exactly out of phase, they interfere destructively and the resultant intensity is 0. On the other hand, when they meet exactly in phase, that is, they interfere constructively, then the resultant intensity is 4 times I naught. Here it should be noted that there is no violation of conservation of energy in the phenomena of interference. The energy which apparently disappears at the minima is actually still present at the maxima, where the intensity is greater than that would be produced by the two beams acting separately. In other words, the energy is not destroyed but merely redistributed in the interference pattern. Now, suppose there is no phase relationship between the two interfering waves, that is, they are produced by incoherent light sources, then the phase difference delta will remain constant for a very short duration of time, which is of the order of 10 to the power minus 10 second, and delta would also vary with time in a random way. In this case, cos square delta by 2 will vary randomly between 0 and 1, and the average of cos square delta by 2 would be half. So, we have resultant intensity I equal to I1 plus I2 equal to 2 I naught, which has been marked by dashed line in this I versus delta plot. Thus, for two incoherent sources, the resultant intensity is the sum of the intensities produced by each one of the source independently, and no interference pattern is observed. Now, I will discuss what are the various conditions that should be satisfied to get stable or stationary interference patterns. So, to observe the well-defined interference pattern experimentally, the experimental setup must fulfill the following conditions. Number 1, the two interfering beams must originate from the same source of light. This is essential for producing stationary maxima and minima. Since for stationary maxima and minima, the phase difference delta should not vary with time. That is, the initial phase difference between the interfering wave must be 0 or constant. The sources producing this type of waves are said to be coherent. Two independent sources can never be coherent. This is because light from any one source is not an infinite train of waves, and there are sudden changes in the phase occurring in every short interval of time of the order of 10 to the power minus 10 second. However, two coherent sources can be accomplished experimentally from single source by either making one source image of the other by reflection, or by dividing the light waves into two parts by reflection or by refraction or by partial reflection. In these circumstances, any change of phase which the original light wave undergoes is shared by its two parts instantaneously, with the result that the phase difference between the waves remain constant, and hence the position of maxima and minima remain stationary. The second condition which the sources must satisfy is that the waves must have the same period and wavelength. Also, their amplitude must be equal or very nearly equal. Third condition is the original source must emit light of single wavelength, that is monochromatic source. Fourth, the two interfering waves must propagate almost in the same direction, or the two interfering wave front must intersect at a very small angle. In the interference experiment, the conditions 1 to 3 will be satisfied if the interfering beams of the light are obtained by dividing the light of a single source. This can be achieved either by division of wavefront or by division of amplitude. Thus, the interference experiment may be divided into two main categories. Number 1, the experiment based on division of wavefront, and number 2, the experiments based on division of amplitude. In the former class, the wave front is divided laterally into segments by mirrors or slits. In the latter class, the amplitude of the incoming wave of light is divided into two or more parts by partial reflection and refraction, resulting in two or more beams which are made to reunite to produce the interference effect. I will describe some famous experiments of both classes. So, first I will discuss some of the experiment which is based on division of wavefront. So, first experiment which I will discuss is a famous Young's double slit experiment. In this experimental setup, monochromatic light of wavelength lambda is allowed to pass through a slit S and then through two slits S1 and S2, which are equidistant from S as shown in this figure. The slits S1 and S2 are perpendicular to diagram and parallel to each other. The two sets of cylindrical wave front emerging from the slits S1 and S2 interfere with each other to form interference pattern on the screen AC placed at some distance in front of the plane containing two slits. If we examine the light on the screen, we see evenly spaced bright and dark bands which are known as interference fringes. Since the path S1 equal to S2, the wavelets arrive at slits S1 and S2 at the same instant. Therefore, secondary wavelets diverge to the right from slits S1 and S2, which have precisely equal phases at the start. Furthermore, their amplitude, wavelength and velocity are also equal. Now, let us determine the positions of maxima and minima on the screen. On the screen, point O is equidistant from S1 and S2. Let us consider a point P on the screen at a distance x from O. If the point P is such that S2P minus S1P is equal to n lambda, where n is equal to 0, 1, 2, 3, etc., then the disturbances reaching the point P from two sources will be in phase, and hence the interference will be constructive, leading to maximum intensity. On the other hand, if the point P is such that S2P minus S1P equal to n plus half lambda, again n is equal to 0, 1, 2, 3, etc., then the disturbance reaching the point P from the two sources will be out of phase, and therefore the interference will be destructive and the intensity will be minimum. Since the point O, we have S1O equal to S2O, both waves will arrive at O in phase. Therefore, if point P coincide with O, the intensity will be maximum. As the point P moves up and down on the screen starting from point O, the magnitude of the path difference S2P minus S1P increases, and hence the condition for maxima and minima will be satisfied alternatively. If we calculate the phase difference delta at any point, we can find the intensity at that point using the equation I equal to 4a square cos square delta by 2, where a is the amplitude of the interfering waves. So now it remains to evaluate the phase difference in terms of the distance x of the point P on the screen from the central point O, the separation d of the two slits, and the distance d, capital D, from the slits to the screen. This can be obtained with the help of this figure. If the point A on S2P is such that S1P equal to AP, then S2P minus S1P will be equal to S2A. In the experimental setup, capital D is much greater than small d and capital D is much greater than x. Hence, angle theta and theta prime are very small and practically equal. Under these conditions, triangle S1A S2 may be regarded as a right triangle, and the path difference becomes d sin theta prime equal to d sin theta. If theta is small, we have sin theta nearly equal to tan theta, so path difference delta will be equal to d sin theta will be equal to d x divided by capital D, and the phase difference delta will be equal to 2 pi by lambda into path difference. Now for intensity to be maximum, delta should be an integral multiple of 2 pi, which will occur when the path difference is an integral multiple of lambda. Hence, for maximum intensity, x into small d divided by capital D should be equal to 0, lambda, 2 lambda, or in general equal to n times lambda. So, the position of maxima xn will be equal to n times lambda into capital D divided by small d, where n is equal to 0, 1, 2, 3, etc. The minimum value of the intensity will occur at those points where delta is equal to pi, 3 pi, 5 pi, so on. For these point, the path difference x into small d divided by capital D will be equal to lambda by 2, 3 lambda by 2, like that, that is in general n plus half lambda. So, the position of minima xn will be equal to n plus half lambda into capital D divided by small d. The whole number n which characterizes a particular bright fringe is called the order of interference. Thus, the fringes with n is equal to 0, 1, 2, 3 are called the 0, 1st, 2nd, etc. order. We can calculate the distance on the screen between two successive bright fringes and between two successive dark fringes by evaluating xn plus 1 minus xn using the expressions of xn x corresponding to bright and dark fringes. This distance is known as fringe width W. In both cases, we get fringe width W is equal to xn plus 1 minus xn equal to lambda into capital D divided by small d. Since the value of fringe width W is constant, on the screen we observe equally spaced dark and bright fringes. Thus, fringe width varies directly with slit screen separation capital D, inversely with the separation of slits small d, and directly with the wavelength lambda of light used. Now, I will discuss some other operators which are based on division of wave fronts. Now, soon after the double slit experiment was performed by Young, The objection was raised that the bright fringes he observed were probably due to some complicated modification of the light by the edges of the slit and not to true interference. Later, Fresnel brought forward several new experiments in which the interference of two beams of light was proved in a manner not open to the above objection. In the following, I will discuss some experiments in which two interfering beams are obtained by refraction and reflection of light. So, now I will discuss the Fresnel biprism experiment. A biprism is essentially two prisms, each of very small refracting angle alpha, placed base to base. In reality, the biprism is constructed from a single plate of glass by suitable grinding and polishing it. The obtuse angle of the prism is only slightly less than 180 degree and the other angles of the order of 30 degree are equal. In the experimental arrangement, the biprism is so adjusted in relation to the source of light that the two halves of the incident wave front suffer separate simultaneous refraction through biprism. Hence, this single prism is termed as biprism. The essential idea is to divide the incident beam into two interfering beams by utilizing the phenomena of refraction. In this experiment, light from a narrow slit S illuminated with monochromatic light of wavelength lambda is allowed to fall symmetrically on a biprism. The intersection of two inclined faces forming the obtuse angle must be adjusted accurately parallel to the length of the slit. In this figure, the slit S is perpendicular to the plane of the diagram. Under this condition, the edge B divides the incident wave front into two parts. Firstly, the one which in passing through the upper half ABD of the prism is deviated through a small angle toward the lower half of the diagram and appears to diverge from the virtual image S1. Secondly, the one which in passing through the lower half CBD is deviated through a small angle toward the upper half of the diagram and appears to diverge from the virtual image S2. The two emergent wave front which intersect at a small angle are derived from the same wave front and hence the fundamental condition of the interference is satisfied. The virtual images S1 and S2 being the images of the slit S function as coherent sources in this experiment. As a consequence, interference fringes are observed on the screen in the overlapping region EF of the two emergent beams of light. If S1 S2 is equal to D and capital D is the distance between the plane of S1 S2 and screen, then like double slit experiment we can obtain the expression for fringe width W is equal to capital D lambda divided by small d. Now I will discuss another important experimental setup which is known as the Fresnel double mirror experiment. In this experiment of Fresnel, to obtain the sustained interference effects, the incident wave front is divided into two coherent interfering wave fronts by utilizing the phenomena of reflection. In this experimental setup, two optically plane mirrors OM1 and OM2 are mounted vertically inclined to each other at a small angle theta and touching at the point O. The light from a narrow slit S illuminated with monochromatic light of wavelength lambda is allowed to fall on the mirrors whose line of intersection through O must be adjusted parallel to the length of the vertical slit S. One half of the incident wave front is reflected from OM1 and appears to diverge from the point S1, which is consequently the virtual image of the source slit S in OM1. The other half of the incident wave front is reflected from OM2, giving rise to an image S2 of the source slit S. Obviously, S1 and S2 are the virtual coherent sources in this experiment, since both are the images of the same source slit S. Thus, the fundamental condition of interference is again satisfied here. Furthermore, since the angle theta between the mirror is very small, the separation d between the coherent sources S1 and S2 given by d is equal to 2a theta, where OS is equal to a, is also very small. Thus, the condition for the observation of widely spaced interference fringes is also satisfied. The light on the screen AB appears to come from two virtual coherent sources S1 and S2, and in the region EF where the two beams overlap, interference fringes are observed parallel to the slit. Now, let us discuss another important experiment which is known as the Lloyd mirror arrangement. In this arrangement, light from a slit S1 is allowed to fall on a plane mirror and grazing incidence. The light directly coming from the slit S1 interferes with the light reflected from the mirror, forming an interference pattern in the region BC of the screen. In this experiment, the central fringes at O cannot be observed on the screen L1, L2 unless it is moved to the position L1 prime, L2 prime, where it touches the end M2 of the mirror, because here light is received only from S1. If the central fringe is observed with white light, it is found to be dark. This implies that the reflected beam undergoes a sudden phase change of pi on reflection. Consequently, when the point P on the screen is such that S2P minus S1P is equal to n lambda, where n is equal to 0, 1, 2, 3, etc., we get minima, that is destructive interference. On the other hand, if S2P minus S1P equal to n plus half lambda, where n is equal to 0, 1, 2, 3, etc., we get maxima. Thus, this experiment provides an experimental confirmation of the fact that a sudden phase change of pi occurs on reflection in a rarer medium, that is from the surface backed by a denser medium. The mirror employed here should have silvering on the front surface to avoid multiple internal reflections, and its surface should be adjusted so as to make it exactly parallel to the vertical source slit S1. So, now I will discuss the interference with white light. So, earlier in the Young's double slit, Fresnel biprism and double mirror experiments, we have considered monochromatic light of single wavelength to obtain large number of bright and dark fringes. Let us now study the changes produced in the fringes when the monochromatic light source is replaced by white light in these experiments. White light consists of wavelengths varying from 4000 to 7000 angstrom, that is from the violet to the red end of the white light spectrum. In the experimental setup, at any point P naught situated on the perpendicular bisector of the coherent sources S1 and S2. The geometrical path difference is 0 for the interfering light waves of all wavelengths present in the white light. Here we get the light of every color in exactly the same proportions as it exists in white light. As a consequence, the resultant illumination at P naught due to superposition of 0 order or central bright fringes of all the wavelengths is white. The spacing between the constructive bright or dark fringes W is equal to capital D lambda divided by small d is a function of wavelength. Obviously, the smaller the wavelength, the closer will be corresponding fringes. Since lambda of violet end of visible spectrum is least, therefore, the condition of constructive interference, that is path difference is equal to lambda, will be satisfied for the violet color and then for other colors in the spectral order. As you move away from the central fringe, as a consequence, the bright fringe nearer to the central fringe shall have a strong violet tinge, followed by other bright fringes having a strong tinge of colors in the spectral order. In reality, no bright fringe is of saturated spectral color. After 8 or 10 fringes, the path difference becomes so large that the condition for constructive interference path difference is equal to n lambda may be simultaneously satisfied for a number of wavelengths. For example, we have the relation path difference is equal to 5 lambda 1 equal to 7 lambda 2 equal to 9 lambda 3, and also at the same point the condition for destructive interference path difference is equal to n plus half lambda may be simultaneously satisfied for many colors. As a consequence, for large optical path difference, the dark fringes of some wavelengths are completely masked by the bright fringes of other wavelength. Thus, with the white light we get a white central fringe at the point of 0 path difference along with a few colored fringes on both the sides, the color soon fading off to white. Now, I will discuss what will happen if we put a glass plate in the path of one of the interfering beam. So, let us take the example of the Young's double slit experiments. So, suppose T is the thickness of the transparent plate and it is introduced in the path of one of the interfering beam as shown in this figure. From the figure it is clear that a light wave travelling from S1 to P has to traverse a distance T in the plate, while the rest S1 P minus T it traverses in air. Thus, the time required for light wave to reach from S1 to the point P is given by T equal to S1 P minus T divided by C plus T divided by V, where C and V are the velocities of light in air and plate respectively. So, capital T time taken by the beam, capital T will be equal to S1 P plus mu minus 1 into T divided by C, where mu is equal to C by V is the refractive index of plate. The physical interpretation of this equation is that due to introduction of the plate, effective path from S1 P to P becomes S1 P plus mu minus 1 into small t in air. Similarly, the effective path from S1 to O, the point equidistance from S1 and S2 become S1 O plus mu minus 1 into small t in air. Thus, when the plate is introduced, the central fringe corresponding to equal path from S1 and S2 is formed at the point O prime, where S1 O prime plus mu minus 1 into small t equal to S2 O prime. From the geometry, we can show that S2 O prime minus S1 O prime equal to d into O prime divided by capital D. So, mu minus 1 into small t will be equal to d into x divided by capital D, where O prime equal to x. Thus, the fringe pattern shift by a distance x equal to capital D into mu minus 1 into small t divided by small d. By using white light, we can measure the displacement x in the central fringe on introduction of thin transparent plate, and with this measured value of x, we can determine the thickness of the plate by using the above expression for x. Now, let me summarize what I have discussed in this lectures. So, in this lecture I have discussed what is interference and what is the basic conditions that must be fulfilled to get the stationary interference pattern in the laboratory, and we have discussed how to get the two coherent sources to get the interference pattern, that is the division of wavefront and the division of amplitude. And we have also discussed some of the famous experimental setup which are used in the laboratory to get the stationary interference pattern based on division of wavefront. In the next lecture, I will discuss some of the experimental setup which are based on division of amplitudes.